Buckling example 1. So in this example, we want to investigate a effect of buckling in two different columns with the same cross-sectional area with the same height. So this example just says consider having two columns with the same material. So elasticity modulus is identical. Both are fixed at one end and free at the other. So effective length is it just says effective length for both of them. LE is equal to 2L. If the original length of both of them are L, and it just says a one is circular and the other is with the radius of R, and the other is a rectangle with A times 2A. If their length and their cross-sectional area is equal to each other, so their length and their cross-sectional area is equal to each other, so we want to know what is, and both handling a concentrated load of P at their tops. We want to calculate the ratio of critical load of circular column to the rectangle one. So that's a critical load P critical for circle over P critical for a rectangle. We want to know what this ratio is. So let's in previous video we just derivate the Euler's buckling a formula for both force and stress. So now we just need to use that equation in terms of a force ratio. So if these are the dimension of our first cross section with the length of L, and again this is R, the same length. So we do know P critical, force critical from Euler's equation, that's pi squared times EI over L effective length squared. So let's see how we can approach our problem. So if their length is the same and they are fixed at one end and free at the other end, it just says equivalent length of both of them are identical to each other because they are the same length, and both of them, due to the boundary condition, fixed at the bottom and free at the top. It just goes by 2 times original length of the columns. So the same material, it just says if the first one is brass, both of them are the same. If this is steel, the other is steel, E is identical. If this is brass, this one is brass too. So the material are identical to each other. Mhm. So if that's the case, we can easily cancel out the effective length from the critical force equation, and because the material are the same, we can cancel out I. Pi squared is a constant, so we just will be left with a just a, sorry, we can cancel out E because of effect of E, and then we are just left with the ratio of moment of inertia for the circle to the a rectangle. So let's see how that goes. So a buckling force ratio of a circle to uh, a rectangle is just a ratio of their moment of inertia. So we do know moment of inertia for a circle at any axis is equal to 1/4 of pi r to the force, and For a rectangular cross section with the length, height, width of B and height of H, which is A and 2A for uh, our problem based on the problem statement. Ix goes by 112 base cube height and a Iy is goes by 112 H cube base this time. And you can easily know Iy is far below than Ix. Why is that? Because Iy is just keep this small b to the cube in rotation, but Iy it just goes by a rotation of the longer h. So that's h cubed. So we do know in buckling, the note buckling occurs at the Vickers at the Vickers axis. So when it occurs at the Vickers axis, Iy is definitely the Vickers axis. So we need to replace the 112 h times base cubed. And for the circle, there is no difference because both of them are identical to each other. So the ratio of their moment of inertia is just for the numerator is a quarter of pi r to the fourth, and for the rectangle, it just says if you want to observe area of both of their cross-sectional area are the same. So for rectangle, that's pi r squared is equal to 2a squared. So that says that the ratio of r squared over a squared is 2 over pi. And if you replace that in the equation for the ratio, you can easily get after simplification, you get a 3 times r squared times a squared. If you replace it from here, it just bring 2 pi here, and that's the ratio of critical force of a circular cross column to a critical force of a rectangular one is 6 over pi. So again, that's due to Euler's buckling formula. That's a 6 over pi. If you divide it by their cross-sectional area, you can get there also the ratio of their stresses. Thank you.